Good morning, everyone. I'm Sandeep Sunkovilli, and today we are going to see the poster presentation of my paper, Analog Hardware Trojan Detection. So, in my poster, as you can see in the introduction, I have uh, briefly talked about my problem and goal. So, the problem is with increasing demand for semiconductor industry, the manufacturing of the semiconductor devices is outsourced, and this raises to security concerns because of the hardware Trojan insertion at manufacturing level. So the goal of my work is to show the effect of A2 analog Trojan on FPGA board and why the present detection technique will fail. And you can clearly see I have kept a picture of the hardware Trojan, of a general hardware Trojan, what it can do. It just bypasses the crypto hardware. So the next part is the hardware Trojan classification. So the reason we selected analog Trojan is because there isn't much work done on analog Trojans when compared to digital Trojans. Even though you can clearly see in the picture that analog Trojans are considerable part of Trojan classification and they can even do a lot of harm. So the analog Trojan which is chosen here is an A2 analog Trojan. So in this you can see there is an input called trigger input and there's called output called trigger output, which is common for every Trojan. So the trigger input, so this Trojan works on the principle of switching capacitance. So the trigger input is connected to a toggling wire and output is connected to a privilege escalation bit. So in our experiment setup, the privilege escalation is created by introducing a glitch into an SDLK signal of a temperature sensor on a Nexus A7 FPGA board. So the fourth part is the results part. So in the results, if you can see, the blue line is the SDA data line, which passes the address and temperature reading information, and the yellow line is the SDLK signal, which helps in reading the information. Even when both the pictures of the oscilloscope are taken at the same temperature measurement, the top one is where Trojan is not active, and the bottom one, the second picture, is taken when the Trojan is activated. And you can clearly observe that the data line is being changed according to the SDLK line. So R2D2 is the most prominent technique available outside for an A2 analog Trojan detection in ICs. And in this detection technique, a certain signals are guarded and an interrupt is generated when these signals are toggling above a threshold frequency. And this detection technique will fail because first thing is we cannot guard all the signals on an FPGA board. Even if we guard the SDLK signal, when the glitch is introduced, the toggling is reduced here than the usual values present. So it will be always below the threshold value of the toggling. And so the conclusion is that in this paper, the effect of A2 Trojan on a sensor with IT communication in FPGA is shown, and it is also shown why R2D2 detection will be failing in this particular scenario.